different circuits configurations. One is common gate configuration. Another one is emitter follower configuration. Emitter follower, we have on with the BJT. The same thing is going to repeat with the JFET. Okay. So I am starting this session. Firstly, we have the common gate configuration. So in the common gate configuration, as you know, if gate is common, the gate terminal will be grounded. So this is the particular circuit. You can see that gate terminal is directly grounded. And if you see, if you want to give the input, gate is the common point for the input and the output. We will be giving the input between source and the gate, and we will be taking the output between drain and the gate. Okay. And also, okay, so you can see that this thing the common point between the with the input and the output is the gate. Between the source and the gate, we will be giving the input, and between the drain and the gate, we will be getting the output. And also we have a VDD. There is a DC source here. Okay, there is only one DC source here. You must notice this. Okay, now we will go for the AC analysis directly. Okay, because whenever we are talking about the amplifiers, we will do the AC analysis. That means we will short circuit the capacitor, we will short circuit the voltage sources, and we will be plugging in the AC source alone, and we will be start to derive the input impedance, output impedance, and the voltage gain. Okay, so right away we are substituting the equivalent circuit of JFET in the common gate configuration. Here you can see, and one mistake is here, because the C1 and C2 should be grounded actually. I mean, it should be short circuited here, but it is not properly short circuited here. You must short circuit here because this is a AC equivalent model, so capacitor will definitely get short circuited. Okay, and also you can see that between the source and the gate we have this VGS. If you just refer the previous AC equivalent circuit for JFET, there will be gate, and gate in the left side, and the right side and the bottom you will be having the remaining source and the drain drain element. Okay, I mean the drain and the source element. In the top you will be having the drain, and at the bottom you will be having the source. Okay, in the same way it is being connected. You can just check the AC equivalent circuit, and here you must be noticing that VGS is here. Okay, this is very crucial. You have to write this clearly. You must be very clear of what you are doing. Okay, and the source terminal is connected to, and the source terminal is connected to, and the drain terminal is connected to the resistor RD. And here it must be noticed that the voltage source VDD is actually short circuited because this is a AC equivalent circuit. So the voltage sources, the DC voltage source VDD is short circuited here. Okay, and this capacitor must be also short circuited. Okay, okay. So as like our previous circuits, finding the input impedance is not as easy as we think in the common gate configuration, because there is a standard connection between the input side and the output side. You can clearly see that there is a connection between the input side here and the output side through this circuit. There is a real connection is there. So we have to be very careful. We have to put some effort to find this input impedance. So first we are loading. Yes. First, we will take that circuit, only this part of the circuit. I'll just highlight it. Okay, I'm from here you should notice that here it is zi dash, zi in the prefix you have the prime, zi prime. So I am taking, starting from here, I am taking this complete circuit, okay, and I am ending through this, okay. So this is the endpoint, okay. I am starting from the node A and I am traveling through the equivalent circuit, AC equivalent circuit, and I am ending at the ground. So here, if we for this highlighted circuit, if I find the equivalent impedance of Zi dash, I mean Zi prime, then I can compute the complete input impedance of Zi, where Zi will be equal to Zi will be equal to Rs parallel with Zi prime. Okay. For that, I want to find the Zi prime first. Okay. So I am moving on to the next slide. Okay, you can clearly see that the highlighted circuit is going to be redrawn on the next slide. Okay, you don't have to remember anything, just do what is given here. Okay. Okay, this is the circuit. This is the redrawn circuit for Zi dash, for determining the Zi dash, and we have assumed that for Zi dash we have the input for finding the Zi dash. We are assuming an imaginary input of V prime, and I prime. Okay, where Zi prime is equal to Zi prime means Zi dash will be equal to V prime divided by I prime. Okay, that is what we are going to find. Okay, ultimately we need an equation which has only V prime and I prime. Okay, other everything should be a constant. Fine. Okay, now we are straight away we are going for, yes. Here we can see that Zi prime is V prime divided by I prime, and V prime, if you compare with VGS here, VGS, the terminals are minus and plus here. If you check this is plus and this is, here it is minus, whereas for V dash it is the exact opposite. Here it is in the top it is plus and here it is minus. So I can write V prime is equal to minus VGS, or I can write as VGS is equal to minus V prime. Okay, the first part is done. Okay, now we are moving on to the next part. Apply the KCL in node A. Okay, see whatever things are there, you apply it. Okay, KVL, KCL, or anything. Here we are ending up. Here we are intuitively we can say that there is a node here, and we have a current. We have a current source here. Okay, and we have a current coming inside this node, So consider this node A. I'll erase it. Okay, consider this node A and apply the KCL. Okay, now we can see that the incoming current is I dash and GM into VGS. Okay, I dash is incoming, and GM is to VGS current is also incoming to this node A, and the leaving current from this node A is I into I of RD. I suffix RD is for this resistor RD, this output impedance RD. The current that is passing through this output impedance RD, that current is represented by I of R suffix D. Okay, and that equation is being written here. Okay, that equation is being written here. Okay, and in the next step we just rewrite that equation in the terms of you just take this you just replace this IRD, I mean this VGS with minus V dash. You just replace this VGS with minus V dash. Here we have that relationship. VGS we are replacing with minus V dash. Okay, and we are ending up with this relation, and then apply the KVL now. Okay, KVL can be applied from here to here. Okay, KVL can be applied here. Okay, starting from V dash, and we are traveling through, this is the voltage. This is the voltage VRD. the voltage drop across this point is VRD. So I am writing minus V prime minus VRD, and finally we have to pass through this resistor as well. So across this resistor RD, we have the voltage drop of VR suffix D. Okay, so we are writing minus VR suffix D. We have to somehow get these two equations to work it out, and we want to find the Zi dash. Okay, now VRD, we know that VRD is the voltage drop across the resistor small rd, and there is a resistor capital RD. Okay, so that can be written as IRD, I suffix small rd into RD, because VRD is equivalent to IRD suffix RD into RD, and for VRD, V suffix capital RD, the current through that that is a voltage drop across the resistor capital RD, and that voltage drop can be represented as the resistor RD into the current that is passing through the resistor RD. That means the current passing through that is I dash, because I dash is coming inside this node A, and while leaving the node, while leaving the network, it will be the same. You just check the KCL here, it will be the same. So that's why it is I dash, still it is I dash, I prime. So we are going to now substitute this equation 1. So on substituting equation 1, we get from equation 1 we have I dash, or IRD, we have the value for IRD, which is equal to I prime minus V prime into GM. So yeah, on substituting that equation, we get here in the place of IRD, we are substituting the equation 1. This is the right arrow. Okay, from equation 1 is being substituted in the place of IRD, so that we will be getting the equation like this. And finally, you take V prime to one side and I prime to another side, so that we will be ending up an expression like this. Thus, we have a Zi prime. We have finally found the Z, that is V prime by I prime is equal to capital RD plus small rd divided by 1 plus GM into small rd. Okay, you have to derive this. This is a very easy derivation. You just want to apply some KVL and KCL, and logically you want to mix the equations. That's it. Okay, finally I'm multiplying 1 by RD in the numerator and the denominator of Zi prime. Okay, so that I will get still more a simplified version of Zi prime. When I'm multiplying 1 by RD in the numerator, we will be having 1 plus small rd divided by capital RD, and while multiplying 1 by RD in the denominator, we have 1 by RD plus GM. Okay, this is the final expression for Zi prime. Okay, so we will be using this Zi prime to find the actual input impedance. See, Zi is your input impedance, Zi prime is your intermediate input impedance only. Okay, fine. Now moving into the next step, we have input impedance Zi is equal to Zi prime parallel with RS. You can really check that in this equation. You can really check that this is the Zi prime we have just found. This Zi prime is actually parallel to the RS. That's why we have the input impedance as RS, Zi prime parallel to RS, parallel with RS, and we are approximating it. Consider that generally your RD will be always greater than, always greater than 10 times RD. Generally it will be greater than RD, but if it is 10 times greater than that capital RD, then we can replace this 1 by RD. Then we can rewrite this Zi prime equation like this. Okay, here we can see that 1 by RD, if RD value is very high, then 1 by RD is very less when compared to GM. And also capital RD divided by small rd, as RD is higher, this capital RD divided by small rd will be very less than 1. So I can rewrite this Zi prime equation as just 1 by RB. Okay. Finally, we can write the input impedance, approximate input impedance as 1 by RB parallel with RS. This is the final approximate equation, approximate expression for the input impedance. Okay. Now we are moving into the output impedance. For output impedance, the first step is make VA is equal to 0. No other go. Just make the VA is equal to 0 while computing the output impedance. Okay. So now just let's go to the previous circuit. Okay. So if I am making VA is equal to 0, then this will become short circuited, and you can see that effectively this VGS, this negative terminal will also come to the ground. That means VGS will be equal to 0. VGS will be equal to 0. So we have GM into VGS also will be equal to 0 in the circuit. Okay. So we can write that expression as, you just check it. Effectively, if I am making this VA as 0, this effective resistance here, it will be 0. So the source terminal will be grounded along with the gate terminal. So this VGS will be 0. This VGS here will be 0. And because of this VGS here is 0, we don't have this current source here, because VGS is equal to 0. GM into VGS is also equal to 0. Okay. Fine. Moving to the output impedance slide. Okay. This is the one I was just talking about. Okay. And on seeing that network, we can directly say that Z0 is Z output, that is the output impedance is capital RD parallel with small rd. You just check that circuit and apply the conditions, whatever conditions is required. You can easily find that output impedance. Okay. Now on approximation, generally this RD is generally RD is considered to be higher than capital RD. So since RD, small RD and capital RD are in parallel, we can replace capital RD parallel with small RD by capital RD, because RD is very higher in parallel connection. Okay. So we can replace that with a smaller resistance. Okay. Okay. Now this voltage gain is something of major concern here. In book, they have followed a method. I think the method we are going to discuss right now is completely different from the book, and you can follow whichever method you feel very convenient. Okay. This is the voltage gain. Voltage gain is nothing but AV is equal to output voltage by input voltage. Okay. Somehow we need to find this output voltage and input voltage. So what I just thought is, we haven't disturbed the circuit much while computing we haven't disturbed the circuit at all while computing the input impedance, intermediate input impedance of Zi prime. Zi prime, you can just check. For that, the expression we have found, this final expression we have found is this. Okay. Where Zi prime is V prime divided by I prime. So when I check what is this V prime, we can easily say that, I'm going to the previous slide. Yeah. Here you can see V prime. The V prime here is nothing but your input voltage. We'll check the actual circuit now. Better to take this circuit. Okay. I'm copying this circuit for explanation here. Okay, fine. Here if you check this This is the circuit you have in mind. Just to paste it here. Just having it here. Yes. Is any problem? Okay. You just have that circuit in your mind. It is very simple derivation. I think I'm done with the input and the output impedance. Okay. So here, this term V dash, that means V prime, V prime and I prime. Okay. V prime, if you check that with the circuit, V prime is actually equal to your VA. Okay. V prime and VI are same. Okay. In the denominator, in the numerator, we have VI. We almost have this VI. Okay. So in denominator, somewhere we need to get that V output. Then only we can say that V output by V input is equal to voltage gain. Yes. Yes. Yeah. Who is this online? Please mute yourself. Okay. So we are going to the next one, and we want to find the voltage V naught. V naught, if you check that with that circuit, it is nothing but V naught. Yes. V naught, if you just check it, it is the current that is being flowing across. It is being the voltage that been dropping across the RB plus and minus. Okay. Who is that? Whose mic is on? Mr. Prabhu, are you online? Why your mic is on then? I have muted it. Okay. If you check the V output, it is a voltage drop that is being that is across this RD. You can clearly see that voltage drop across RD is V output. So you just compare that with this circuit, with the circuit that we have used to determine the ZI prime. The current through that RD is I prime. Okay, the current through that circuit, that current through that RD is I prime. So this is the hint being here. So we have I prime with this. I'll say, since there are a lot of equations are here, the PPT is struggling to load fastly. Okay, fine. Okay, now I have V prime is equal to VI, and we have I prime here. So if I multiply with the capital RD, we can say that it is, if I multiply with the capital RD in the denominator, we can have the V output in the denominator here. In this, I'll say, if I am multiplying with the RD with this I prime, we can get the V output. Okay. So for that, I'm multiplying this RD on both the sides of this equation, both the sides of this equation in the denominator, so that we will be having, okay. In the numerator, we will be having the V input, and in the denominator we will be having the V output. So this is the equation we get once after substituting in the place of V prime. If we substitute VI, and in the denominator we have to multiply RD on both sides. Okay, this is the final equation we just get, and on substituting RD into I prime as V output, we can have V input by V output as this expression. This is the expression we have got for V input by V output. But actually, our voltage gain is V output by V input. So we are going to invert this complete equation. I'll clear this. Okay, we are going to invert this equation so that we will be having V output by V input. The numerator guy will come to the denominator. The denominator will come to the numerator. Okay. So finally, we have this voltage gain is the expression that has been shown here. You can see this expression, and Zi prime will have the same, will have a kind of same arrangement. Okay, fine. Okay, now we have to approximate it, since based on RD, if RD is higher, then this term RD divided by RD will be very less, and here this term will be also very less. So finally AV will be equal to RD into GM. Okay, because this term is very less, so I am approximating it to 0. This term is here is also the same. I am approximating it to 0. So approximately we will be ending up having only this term. These two terms will go off. So this is the approximate value of the voltage gain. Okay, fine. Okay. We will move on to the next circuit, and here you can see that the voltage gain is positive. So far, whatever we have discussed, the voltage gain comes as negative. Here we have the voltage gain as a positive. So that we are going for the common gate configuration. Okay, fine. I'm moving on to the next configuration. That is a source follower or common drain configuration. Source follower configuration. The source follower circuit we have already studied with the BJT. The same logic we are going to apply here. Okay, this is the circuit we have, and this is the JFET source follower. Remember, this is the JFET source follower, and for BJT, what you have is, I don't have a resistor here. I have a resistor here that is being connected to the VCC. Correct? This is the circuit for the source follower of BJT. We don't have a resistor RG here. Instead, we have a resistor RB here that is connected to the base under the VCC. This is the voltage follower circuit. I mean, so voltage follower circuit that is being used and that is being designed with the BJT. Now we are dealing with the source follower circuit. The only difference is we are connecting the resistor. We are connecting this resistor to the ground. Okay, so that we can get the self-bias kind of configuration. So this is the circuit for the source follower configuration. Okay, and we can clearly see that the JFET and the source, the JFET is emitter follower, and here we have source follower. That means in the BJT we are taking the output from the emitter. In the JFET we are taking the output from the source. That is the difference between the JFET BJT emitter follower and the JFET source follower. Okay, and also it is known as the common drain configuration. Why it is? Because during the AC analysis we have to connect the DC source to the ground. So what happens when I am connecting this DC source VDD to the ground? Then we have to give the input between the gate and the ground, and we have to take the output between the source and the ground. That means the drain is becoming the common terminal here. That's why it is also known as the common drain configuration. Okay, fine. I will move on to the next slide. We are going to do the same thing. We are going to substitute the same AC equivalent circuit, and we are going to solve for the input impedance, output impedance, and the voltage. So after substituting, you can see that you can see here this will be short circuited. Okay, this is not grounded. Remember, this capacitor is not grounded. There is a difference between this capacitor. This is the output capacitor, coupling capacitor, and this is also a coupling capacitor. This will not be grounded. Okay, so this RS, this resistor RS will be there always, and resistor RG is connected to the gate terminal. Okay, RS is connected to the source terminal, and the drain is connected to the ground. Okay, because we will ground this for AC analysis. Okay, so that circuit I'll show next slide. Okay, so this is the one. For the gate terminal we have RG, and in the source terminal we have RS. We have just short circuited the capacitance here and short circuited the capacitance here in the input. Okay, so this is the circuit we are going to analyze now. Yes, 1 minute. Okay, now we want to redraw the circuit, because this circuit looks a bit awkward. If you just see, this point here is source. Consider this point, this node here is A. Okay, I'm just naming this node as A. Okay, this point here is B. Okay, so this B point is directly connected to the ground. So this B point will also exist here. This B point will also exist here, because this B point is connected to the ground. So this point and this point are common. Correct? So now I can redraw the circuit. You take this point A to the top. You take this point A to the top, and point B, this line completely to the bottom. Okay, this line completely to the top, this line here completely to the top. You are going to swap this particular network, so that you will be having a network like, I will remove this. Okay, you will be having a network like this. Okay, here you can see this is the A terminal I just mentioned. Okay, and this is the B terminal. Every ground terminal is being brought down. Okay, in this way we can redraw the circuit, and it should be noted that VGS comes like this. Okay, here the VGS is between the gate and the source. Similarly, the VGS should be between the gate and the source, whereas in this circuit we have source in the bottom, whereas here we have source in the top. We just redrawn this circuit, that's all. Okay, now this is the circuit we are going to have for the analysis. Whatever analysis we are going to take, that means the input impedance, output impedance, and the voltage. Okay, the first thing is the input impedance. Okay, first thing is the input impedance. Input impedance is very direct, because there is no connection between the input side and the output side. You are just measuring the VGS. Okay, so input impedance is directly, we can write it as RG. Okay. So output impedance, for making the output impedance, we want to have VA is equal to 0. I am going back to that. If I make VA is equal to 0 here, that means I'm connecting this to ground, connecting this VA to ground. That means this overall, this effect of RG will also get cancelled. That means the positive terminal will connected to the ground, and the negative terminal will remain here, so that we will be having minus plus. The voltage drop across this is VGS. Okay, so this is the circuit we must be having right now. After supplying the VA is equal to 0, so I am redrawing that circuit. Yes, here is that redrawn circuit for computing the output impedance. You can clearly see that. Okay, and now we can see that VGS, the voltage drop across this terminal, these two terminals is here and here, is minus VGS, when I see from this side, when I see from the left side, it is minus VGS, whereas when I see from the right side, it is V naught. So how this V naught and VGS are related is V naught is equal to minus VGS, or VGS is equal to minus V naught. Here we have the relationship between the VGS and the V naught from this circuit. Okay. Now, and then finally we do all the circuits we just want to require. We just want to get that relationship to get the output impedance. As you know, output impedance is V output divided by I output. I mean V naught divided by I naught. So we want some equation which has the term V naught and I naught in it. Okay. For that we will apply KVL, KCL, and all those things. First we will be doing the KCL here. Okay. Here this complete node, this is a complete node. You can just connect it to one point. This everything. Okay. Everything here, every terminal, every leg here, that is the current source here, and the resistance small rd, and the resistance capital Rs, everything is connected to the single node S here, and there we will be applying the Kirchhoff's current law. There we can see the incoming current is Gm into VGS is one current that is incoming to that. I naught is another current that is incoming to it. Okay. And the output currents are the current that is passing through the RD and the current that is passing through the RS, capital RS. Okay. That's why we have this equation. I naught plus GS, this is the incoming current, and this is the outgoing current. Okay. And then for IRD is the current that has been passing through this. I'll remove that. IRD is the current that is being passing through this small rd resistor, and the voltage drop across this resistor is V naught. Okay. So we have this term IRD is equal to V naught divided by RD, and similarly IRS is equal to V naught divided by RS, because the voltage drop across the resistor RS is V naught, and the current and the resistance value is RS. So the voltage drop across this is V naught, current through this RS is V naught divided by RS. Okay, two things are over. Okay, see, I'm taking the derivation directly from the book for this, because in the book itself it is given very fine. Okay, now we are making all the we are doing all the circuits to bring that final output. Okay, so we are bringing I naught to one side. I naught, this equation, this complete equation, you can see I am bringing I naught to one side and V naught to another side. Okay, so that we will be having an equation like this. Here also we are using the relationship VGS is nothing but minus V naught. Correct? From this circuit, VGS and V naught are in parallel but in opposite polarity. So VGS I can replace with minus VGS, minus V naught. VGS I can replace with minus V naught. So finally we have a expression like this. When we substitute it here, we don't even have to substitute it. We have V naught here, V naught this side, we have I naught in the left hand side, we have V naught in I naught in the left hand side and V naught in the right hand side. So you just take V naught by I naught, that will be equal to Z naught. So finally we have this expression 1 by RD plus 1 by RS plus 1 by GM. Okay, that means Z naught is the output impedance is RD parallel with RD parallel with RS parallel with 1 by GM. Okay, and finally on doing the approximation, assuming that RD is higher than this source resistance, by applying the approximation, we will have the output impedance. We will have the output impedances RS parallel with 1 by GM. Okay, so this is about the output impedance. Still voltage gain is there. Okay, for finding the voltage gain is also very direct. You just check this circuit. Okay, circuit. See this circuit, you just take this circuit with you. Okay, you just check what is VI and VGS, VI and V naught, because voltage gain is equal to output voltage by input voltage. So AV is equal to V naught divided by VI. So V naught I want to find first. So for finding the V naught, I want the voltage drop across any of this resistor. Yes, who is that?
அதுதான் unable to connect இது இந்த ப்ராப்ளம் எல்லாம் வந்து
Who is that?
தெரியல.
Yes, I think you have some doubt. Okay, so this is the circuit we are just considering right now. Okay, and in this circuit, if you just check, we want the output voltage and the input voltage. Somehow we need the output voltage and the input voltage to find the voltage gain. So output voltage is the voltage drop across or the voltage drop across RD. Okay, so for that we require what is the current that has been passing through that circuit, correct? So the current we have here is GM into VGS. So we can find the effective resistance of this RD and RS, so that V output will be equal to GM into VGS into RD parallel with RS. Okay, that is the output voltage. Yes, that is the output voltage here. Okay, I'll take that circuit directly. Okay. So this is that circuit. You can see that the voltage drop, the output voltage is nothing but the current that has been passing through this resistor into the effective resistance of this, so that we will be having RD parallel with RS. Here you can see RD parallel with RS, and GM into VGS is the current that has been passing through there. That's why we have V output is equal to GM into VGS, RD parallel RD. Okay. Now we want to have the input voltage. We somehow we want to drag in the input voltage inside the equation. Okay. Now if I for applying the input voltage, the voltage drop across this resistor RG here is VI. So I am applying the KVL here. Okay, from this point we couldn't draw that. Okay, I'm applying the KVL here. Okay, I could approximately make it somewhat. Here I'm applying the KVL for finding the input voltage, so that VI is actually the voltage that is dropping across this resistor RG. That is VI. So the equation can be VI minus VGS minus V naught, because the voltage drop across here is V naught, because V naught is in parallel. In parallel, the voltage drops are same. So here it will be V naught. So VA minus VGS minus V naught. On rewriting that equation, we have VA is equal to VGS plus V naught. Okay. Now substitute the values of now rewriting the equation again. VGS is equal to VI minus V naught. Now this substitute this VGS equation. This equation I will. substitute this VGS equation, okay, here in this equation, so that we will be ending up with this equation here, which has both the terms of output voltage and the input voltage. So take the output voltage term to one side and the input voltage term to the another side, and finally you will be getting the voltage gain as V output by V input is equal to GM into RD parallel with RS divided by 1 plus GM into RD parallel with RS. And also here you can see that in case this RD is higher, or RD value is higher, this is in the parallel connection, RD is in the parallel connection, so RD parallel with RS can be replaced with RS, okay, in the both in the numerator and the denominator. Okay, now finally the overall, if you just check it, this value is approximately equal to 1, or it can be only less than 1. This is the same condition for the emitter follower we were just using, correct? This is the same thing. V output is equal to V input for the emitter follower also. For the source follower also, this is the same thing we are just getting here, okay? And so this is about the source follower. Just try to apply things wisely. Just apply the KVL, KCL wisely, so that you can get all the expressions very easily. Okay, fine. I'm moving on to the next slide. We have very few things to cover in this third unit. Okay, first one is depletion type MOSFET. This is the symbol for depletion type MOSFET. See, for N channel, it is coming inside. The arrow will be inside. Arrow will be coming inside, and for the P channel, the arrow will be coming outside. Okay, this is the depletion type MOSFET we have. Okay, and the equivalent circuit is like this. See, this is the same equivalent circuit as like we have seen for the JFET. Okay, there is no difference between the JFET equivalent circuit and the depletion type MOSFET equivalent circuit. Okay, so we are not going in detail for the depletion type MOSFET, because whatever is applicable for JFET, that is being applied for depletion type MOSFET as well. Okay, and things we have to notice here is Shockley's equation is the same. The same Shockley's equation is being used for the depletion type MOSFET, that is the D MOSFET, and the GM and the AC equivalent for the D MOSFET means depletion type MOSFET. The GM means the value of GM. You can notice that down from the specification sheet, and it is given as YOS or GOS, either the conductance or admittance. Okay, you can directly take the GM from there. And finally, only one difference is there. You have to notice here, only one difference is there. This VGSQ, that means the VGS is actually negative for JFET when you see that, whereas VGS is positive for N channel devices and negative for P channel devices. So this means the value of GM can go beyond GM0, where GM0 is the transconductance when VGS is equal to 0. So GM will be greater than GM0. Okay, whereas previously in JFET we have GM always lesser than this GM0. Okay, this is the depletion type MOSFET we have. Okay, finally we have this enhancement type MOSFET. See, you really have to take care of this symbol, how it is being drawn here, because this arrow and how it is drawn is very, very important. Okay, and here you can see this is the enhancement type MOSFET. In the enhancement type MOSFET, these lines here are broken. Okay, are broken between the three terminals. Okay, for everything there is a reason. Let's not go deep into that. Make sure you draw the proper symbol while writing. Okay, here it is broken, and this is the NMOS. This is the NMOS enhancement type E MOSFET, and this is the PMOS E MOSFET. Okay, here we have the same equivalent circuit. There is nothing changing from the JFET or the D MOSFET. The only thing that will be changing is the voltage, the Shockley's equation. Okay, previously we used the Shockley's equation. Here we have a different equation for it. That is ID is equal to K into VGS minus VGS. TH means threshold, VGS threshold, the whole square. Okay, this is the relationship between the output current and the controlling voltage VGS. Okay, this is the one difference, one main difference between the JFET and the enhancement type MOSFET. Okay, and normally we get the GM by differentiating this equation ID with respect to the VGS. So we can easily derive that equation. We can easily derive that GM just by differentiating this equation here with respect to VGS. Okay, that is what is being done here. We can see that finally we get GM is equal to 2 into V VGS Q. Q is the Q point at the Q point. In the Q point at the corresponding point, we can find the Q, and the VGS threshold minus VGS threshold. This is the final expression of our transconductance for the enhancement type MOSFET. Okay, so these are all the things you have to notice. Okay, so in the sums, mostly you will be given with the data of whether RD is not directly given, GM won't be directly given. That is for sure. Okay, you will be given with GOS or YOS or YFS. You want to find the relationship between them. RD is the actually resistance. So you are given with the conductance. So you have to take that RD is equal to 1 by GOS or 1 by YOS. And GM is the conductance here. YFS is the admittance directly equal to YFS. That is what is written here. Okay, fine. Okay, now for the assignment, you want to solve the example sums, example problems for the things we just covered, because example sums are nothing but you just have to substitute the values of the resistance and the capacitances. Okay, and ultimately you want to compute what is the value of the voltage gain, input impedance and the output impedance. Okay, I will clearly mention what are all the example sums. You have to write it as an assignment. Okay, fine. This is it for today. You can just, I will wait for 5 minutes. You can ask your doubts if you have anything. Okay, meanwhile I will send you this PPT. You can send your attendance. Okay, quickly send your attendance.